I love learning new stuff, and that's why I'm a developer and a complete nerd. And so this XKCD comic, I don't know, it's something that I think about all the time whenever I'm like upset with a colleague because they don't know something, because that's ridiculous. Like, there are things that I don't know. My worldview is that in every room that I step into, assuming there's somebody else in the room, is that I can learn something from that room. This room right here is just rife with things that I've never learned before, and that's cool, and I like that a lot. And so that's what this presentation is. I'm going to talk about things that I discovered at one point or learned sometime, and that I thought was cool, and that I revel in sharing with other people. And the reason I named it Random Access Memories is because that's what I was listening to when the idea came to me. And I decided to like not only have that inspire what I talk about, but how I talk about it. So this Angular app that I put together, it's not going to be linear, one after the other. It's actually going to randomly select from a list of 10 cool things that I'm going to talk about today that are going to be presented in absolutely no order whatsoever. So it'll be kind of fun for me, and hopefully for everybody else that's listening. So
you don't know the order.
I don't know the order, and you can actually review the code after the fact to call me on that. Because
challenge yourself as a presenter.
heck yeah. I'm gonna do it. I'm looking at this.
With one man behind my back.
So Chris, it's very important while we're doing this, don't refresh the page because it will lose everything, especially the order so far. But the let's go button at the bottom is what I'm gonna have you click to move to the next one. And then it's gonna be a next button that'll cycle us through. So I'll give a call out when we move between. The entire, last thing I'm gonna say before we dive in, the entire point of this presentation is exposure. I'm not going to explain these concepts to the point where you'll understand or it'll make sense. At least I don't think I will. But I'm going to leave you with breadcrumbs that you can follow up on later. I'm going to convey the essence of why I think this is really cool and then spend no time actually explaining how it works. Sounds fun?
Yeah.
All right, let's dive in. So, okay, so what we're talking about here first is going to be Russell's paradox. What's your favorite paradox? Because Russell's paradox is my favorite paradox. It is, does the set of all sets that do not contain themselves contain itself? The answer is obviously yes, because it contains all sets that don't contain itself, so it must contain itself. But the answer is also no, because it's a paradox, right? You see how it works? It's very simple, and I'm not explaining it very well, but I just said that I'm not going to do that, so I'm not going to worry about it too much. To the right, in the top right, that is the formal explanation of it. It's very, very simple. It says let big R be the set of X such that X is not in X, then R is in R, if and only if R is not in R. So it's really weird. It's this very simple mathematical statement that does not add up. There is a way to explain why it actually makes sense, but you need a much higher degree than what I have, so that's okay. But this paradox is very cool because, for me at least, I read it once, it resonated with me, and then I returned to it over time to like kind of to pick at it, to maybe understand it a little better. And part of that understanding is looking at the person who came up with it. It was Bertrand Russell, a famous thinker of the early 20th century. And he wrote on a lot of different topics, not just mathematics. One of the topics that he wrote on was theology, and that led to me reading one of the most important quotes that I've ever encountered, which is second to last paragraph there. The good life is one inspired by love and guided by knowledge. Neither love without knowledge nor knowledge without love can produce a good life. And that just means a lot to me. And I use that as sort of my North Star and guiding principle. And like, I never would have stumbled across that if I didn't find an interest in this particular paradox and repeatedly go back to it to try and learn more about it. I think that's pretty cool. I'm glad this is the one that we started with because it's one that's very close to my heart. And then this meme is hilarious, and I think applies very nicely to the paradox. All right.
I love how he puts it, this meme is hilarious, other is factual.
True. All right, let's go to the next one. Okay, I added this one this morning. This is great. Has anyone here ever heard of a video game called World of Warcraft? Couple people. Cool.
Who hasn't?
Yeah, right? So online gaming actually started much earlier than you might think. In the late 70s, there were these things called multi-user dungeons, or MUDs. And that is what led to what we know as today as the MMORPG, or the thing that caused me to fail out of college the first time. So early in the game's life cycle, there was a dungeon called Zul'Gurub, and it's about the trolls and stuff in their story that I never paid attention to. The final boss in that dungeon is Hakar the Soul Flayer. And you'll probably wonder why I'm telling you this. It'll make sense in a second. He had an ability called Corrupted Blood. And it was this thing that would be applied to a player or some sort of entity, a player's pet or something, and it would deal damage over time. And then if that character died to that damage, they would explode and spread it to everybody else around them. And the developers had planned this to be something that happens in the fight. So you have to like position and make sure you're not next to your teammates or something so that you could kill a boss. And it was effective. It was a challenging boss fight. What they didn't expect is that through clever use of gameplay mechanics, you could bring that debuff out of the fight arena into populated city centers and start spreading it to unsuspecting players, low-level characters that should be nowhere near the boss. So what's interesting, this is a legit picture from the server when that happened. Those are all corpses of players. The cities were uninhabitable. You couldn't go anywhere because this thing would spread to you. Epidemiologists used it as a model for learning more about pandemics and human behavior towards them. This was well before COVID, so I'm sure it played into that in some way. But that is so interesting. Like, something about this story, like it came up in a podcast that my wife was listening to, and it's out there. It's one of those cool ways where like emergent behavior can be used for things that you never even thought that it would be used for. And like, well, I really like the car boss fight, so that's why this one really resonates with me. So, okay, so this one is also, these are all my favorite. This one's gonna be hard to talk about because basically it's just an advertisement for an article that I think everyone should read at least one time in their life. There's a website called Wait But Why, and I'm sure they have other content on there, but there's this one pair of articles that I find most interesting. The author, whose name I should probably know, but I don't, I apologize, starts from the number 1 and moves up to the largest mathematically relevant number ever, called Graham's number. And like, Graham's number is a big number, understatement of the century. It is bigger than what we can comprehend as humans. So what I'm saying is like, think of a number, okay, well, let's put it this way. If I say, think of a number, and then I use words to describe it, the end result, you would not be imagining Graham's number. It is not possible. This is the type of number that sequence that you can use to build to the number earlier on in that sequence, G1, right? These pictures won't make sense, but if you read the article, they'll make sense. G1 right down here, 4 upward arrows, and then another 3. You've got the concept of like addition, multiplication, exponentiation. That's like tier 3. Continue all the way up to tier 6. I think I broke this down, right? So we go from exponentiation to tetration, which is iterated exponentiation, to pentation, which is iterated tetration, to hexation, iterated pentation. That's what 4 upward arrows means. So 4 upward arrows to the 3 is a number that is impossibly large. This number, there are more digits in this number than there are atoms in the universe. This is a big number, and that's G1. In order to get from G1 to G2, G2 is very similar to G1, but instead of 3 with 4 upward facing arrows, it is 3 with G1 upward facing arrows. So what Graham's number does is it takes the concept of iteration and iterates it 64 times. Graham's number is G64, which is 3 with G63 number of arrows, and then another 3. This number is massive. Words do not exist that can describe this number. And the article is fascinating because the first part starts with 1 and to 10 to 100 and uses dots. And then along the way, it discards dots because it's no longer feasible. And then when he gets into Graham's number, he uses these things called Power Tower Feeding Frenzy Cycle Festivals, which is like, you take a 3 and then you put it to the 3, and then you do the same thing again, and you continue until the pile of 3s is 150 kilometers long and it reaches the sun, right? You go up to the top, because that's the cool thing with how this works, is like you start up at the top, you take 3 to the 3, and then you move down, and so on and so forth. If you're up by the sun and you work with 4 of the terms, you've gotten to G1, and you're only like less than a meter away from the sun. You need to work all the way down back to the earth, 150 kilometers of these terms. This is a big number. And what's cool about it is it actually means something. Graham, the guy who came up with it, it's used in a proof for something that I don't understand. I was going to put the words here, but I decided not to. It answers some question. So it's not like this is just a big number, because big numbers are cool, which they are, but it actually serves a purpose, and that's why I think it's cool, and it's just fun to read about. This is one article that I return to every couple of years because it's just a blast to read through. I didn't mention, but on every page there's a would you like to know more? And when we're done, I'm going to have Chris post this into Slack so you can follow up on any of these things. Probably something important that I should have said, but stuff like this is going to link you to the article so you can read all about it if you are so interested. Let's pop to the next one.
Any idea why that stopped at 64?
It has to do with what the number is actually doing. It's like the map problem with like how many squares of different colors you can have on a map, something like that. That's the kind of problem it's solving, but it's much more complex. And I didn't spend a lot of time understanding the reasoning behind the problem because like it's much more interesting to read the article type stuff. But it stops at 64 for reasons, and like the reason that we're not talking about G63 or G65 is because Graham specified this number as There's like an upper bound to the solution to the question that he was asking. Okay, Minecraft. Everybody heard about Minecraft here? Minecraft is awesome, and if you've never played before, you might not be familiar with one of the things in Minecraft, one of the blocks that you can mine called redstone. Redstone is pretty cool. You can use it to create basic mechanisms, I'll say, like a switch that you press a button over here and it flips a switch over here. And you can use this redstone dust, once you mine it, it turns into dust, spread it across the ground and basically send signals back and forth. You might see where I'm going with this. These building blocks you can use to create a computer, and people have. There is a guy whose name I think I included. Nope, sorry, Sammy URI built a computer inside Minecraft that can play Minecraft, which is just the coolest thing ever. And like, I don't know, the stuff that people build in Minecraft blows my mind. I don't have the patience for it, but it's just fascinating to look into. I see you've noticed the funniest part, which is the name of the computer he built is Big Chungus 2. Yeah, there's a cool YouTube video where he walks through, I think, how he builds it and how it works and all that cool stuff. So. It probably uses the same principles. Like, this is an aerial view of like the computer construction. Pretty sure I pulled that from the video or just a related Google search that looked a lot like it. But he breaks it down. He's like, this is the graphical processing unit. This is the other parts. And like, these are all things that are built in Minecraft creative mode. And it's just, it's fascinating.
He recreated Pokemon Red from scratch using that computer.
Isn't that
So you
cool?
play all Pokemon Red.
All right, what's up next? I was hoping it was a different one because it would have played really cool into what you were saying. Wing Commander is a MS-DOS first-person shooter, space shooter, flight simulator video game that was originally released in 1990. It was being written by developers, you know, and they had a deadline, like many of us do. The deadline was fastly approaching, and they had this one bug that they could not figure out, which was when you quit the game, it quit to the DOS prompt, and it spit out this ugly message about error, like memory allocation type thing, and like they, for the life of them, could not get down like how to fix it. So one of the developers, whose name is on here, Ken Demarest, came up with a clever idea. He hex edited the message of the error that was coming out and shown to the user so that it said, "Thanks for playing Wing Commander." And that's how they shipped it. All right, what do we got next? Okay, so this one's not really computer related, but I love talking about it. I actually bring, this is my like go-to party thing, which tells you how fun I have at parties. A sentence that uses every letter in the language that it's set in, so in this case the English language, is called a pangram. So one of the most famous pangrams is the quick brown fox jumped over the lazy dog, and that's used for like typesetting and different things like that because it shows all the characters and stuff. But there are others. In fact, there are uncountably infinite sentences with all letters. But some of the cool ones are the ones that use as few letters as possible. There is no perfect pangram in the English language. You can't have a 26-character sentence that uses all 26 letters. The closest is 28. Waltz, bad nymph, for quick jigs that vex. Other good ones are packed my box with 5 dozen liquor jugs and Sphinx of black quartz, judge my vow. These all make very, very good passwords. Not very secure. All right, what do we got next? All right, sweet. There is a story that I love to tell, and I'm going to tell it right now. It doesn't have anything to do with computers, but that's okay. It's about Wojciech, who served as a Polish army private, eventually got promoted to a corporal, and is a Syrian brown bear. Wojciech is the coolest, and I read a book about him, and my buddy told me the story about Wojciech long ago about how they would bring him along because he carried artillery shells and he was really good at it, and they would feed him beer and cigarettes, and he loved it. It's fantastic. It's such a great story. They got him into, what is it, the word that they use? They like enlisted him because when they went to join the British Army, they had to go and travel on one of their ships, and ships don't allow mascots or pets. So they brought him into the army, and he eventually got promoted for the Battle of Monte Cassino, I believe it's called, where he just, what he would do is he would watch people in his unit and see what they do and just do that, mimic it. So he would generally be walking around on both feet because that's what he saw other people do. They were carrying things around, so he would do that too, and it was just, it's just delightful. I highly recommend looking into Wojciech because it's just a great story. And it's one of those things that I like to talk about whenever I have the opportunity. So.
I'll put out a sentence you have on there. He proceeded to claw his way from the rank of private to corporal despite being functionally illiterate.
I'm glad you shared that. All right. Okay. this one's called Evil Floating Point Bit Level Hacking, based on this comment, because I thought it would probably be uncouth to name it after that comment. So in the 90s, I think, late 90s, if you wanted to calculate the inverse square root, which is 1 over the square root of x, generally you were using lookup tables. This is no longer the case. Computers have gotten better since the late 90s, or so I'm told. So this sort of thing is not a concern anymore, but back in the day it was a pretty big deal. So this team, this is something that's been around and known for different things, implemented several places. Most well known for Quake 3, which is pictured up on the right, and where this code excerpt comes from. What it does is it uses a very clever bit shifting approach to approximate the inverse square root. And it's not accurate. It's about 15% off, but that's okay. They use this that's okay because you can iterate it again using Newton's method to get it to be more accurate. So ultimately it ends up being faster than using a lookup table. This sort of thing was really, really cool for early three-dimensional games because it's used for calculating vectors for light. So this is the kind of calculation that needs to happen a lot. And so the speed of it is very, very important. So things like this, clever little things that make absolutely no sense unless you know what's going on, are really cool. And every time I run into something like that, I just appreciate it. I think it's very awesome. The amount of like understanding and knowledge that goes into actually being able to like produce and come up with something like that is fascinating to me. And then, I don't know, I just like this one. Not much more else to say about that, but it's pretty cool. Never played Quake 3 though. I hear it's good. All right, I think I know what it is. I didn't. I thought it was something else. Okay. Turing and Alan Turing and his machine. So I'm going to talk about it in general terms. I assume we're all somewhat aware of it, but the actual Turing machine concept pictured up to the right is kind of foreign. When you think of a computer, when I think of a computer, I generally don't think of a long string of uninterrupted ticker tape being investigated by something that's looking down on it and the ability to move side to side and write or read, but that's what a Turing machine is. And what's really cool is anything that you can compute with a computer can be done by a Turing machine. It will just take a very, very long time. And so there's this concept of Turing completeness, which can be applied to a lot of things that might be surprising, such as the game state of a Magic the Gathering card game. This guy, Churchill, whose name I didn't put on the slide, but I should have, wrote an incredible paper about how to construct a functional Turing machine using a game of Magic the Gathering. And it's really, really complicated. It's the type of thing that could potentially happen during a normal tournament, but step one is like create 36 copies of a Rotwang Reanimator, so probably not going to happen. But the way that it works is he sets up a cascading set of triggers, thousands, 10,000 of them, that remove all choices from the players. So you can basically program the game. And it continues and plays out based on the rules, based on how you've set up the game state so that it can compute. And because we're talking about creating a Turing machine inside of a Magic the Gathering game, that means that the code that we write day to day for the websites that we create can be calculated and computed by a game of Magic the Gathering. And if that sounds preposterous, I get it, but it is true. And that is how things work. It's pretty wild, right? This is one that's cool to think about and just kind of breaks your mind until you sort of like connect the dots and see how it all fits together. I think we're on to the last one, which is the one that came to mind when we talked about Pokemon. Pokemon Yellow, great game, came out in 1998. Yeah. And I don't know if any of you are familiar with the speedrunning community, but it's pretty cool. GDQ is awesome. Highly recommend looking into some of their runs. But games like Pokemon are just thousands, tons and tons of people will be competing to try and get the fastest gameplay time in a game. And it might surprise you to find out that the fastest game of Pokemon Yellow is under 2 minutes. It's actually under a minute and a half. And the reason for that, and what we're talking about, is the any % category where glitches are allowed. So the trick is you intentionally corrupt the game's memory and set it up so that you can access menus or access a menu that ties to something that it shouldn't, scroll through the menu and select to be instantly transported to the end cutscene, therefore beating the game. Pretty cool, huh? Somebody took that idea and brought it even further and figured out a way to use that same technique, very, very complicated way to use that same technique to perform arbitrary code execution inside of Pokemon Yellow, rewriting the game cartridge to instead boot up and play Tetris through doing nothing but pressing buttons on a Game Boy. Like there's no hacking or accessing the cartridge at all. It's just tricking it into rewriting its own code based on user input. They do this through what's called a taskbot, used for tool-assisted speedruns, where people will like program it in to try and figure out the mathematical fastest possible way to complete a sequence of a game. But as you can see, they use it for some other interesting things. This is a screenshot of what happens like during the thing, and it's bonkers. Like Pokemon runs in particular, if you watch them, they'll start off normal and then they'll go absolutely off the wall. There's one like Pokemon Blue catching all 151 Pokemon that takes just under an hour or just over an hour, but breaks the game in ways that are fantastic. And the GDQ stuff that I talked about, they'll stream, it's an exhibition show. They stream people running games and speed running, and they also talk about like how the community stumbled across these things and how they solved these problems and how they, it's just great. It's fantastic to listen to all this stuff and watch it happen, and I can't get enough of it. That is all of them. So Chris, if you click to the summary there, I set this up. If you Control A and copy all this and then post it into Slack, each of these links in the order that we talked about them today is going to point you to the Would You Like to Know More to get more information about what we talked about. Hopefully, my goal here was that everybody in the room at least like heard something new. You know, maybe you knew 9 out of 10 of these things, which would be awesome. Let's hang out. But hopefully, like, I just want to expose people and talk about how discovery is awesome. And as developers, we have a really cool opportunity to just spend time learning stuff. And I think that's awesome. So thanks for giving me the opportunity to share some things.